Hi everyone, my name is Alice. I'm education lead at ZKM. Today we'll be going through an overview of zkMIPS, its different components, and we'll also be doing a demo of generating and verifying a proof using ZKM's proving service. So in our first part with zkMIPS, we want to answer the question, what exactly is ZKM? So ZKM is a general purpose zkVM for verifiable computation that's based on the MIPS architecture. Our zkVM is called zkMIPS. And what does this mean exactly? Well, let's break down the statement. We'll first start off with verifiable computation. Now, in verifiable computation, one party, like a single user yourself, can outsource the computation to some computationally more powerful party, like some servers in the cloud, and then be able to verify the correctness of the result of that computation that you're trying to outsource. A proof of knowledge helps describe that dynamic. It's a two-party protocol with both a prover and a verifier. So the prover is typically the computationally more powerful party, which in our case is like the servers in the cloud, and the verifier is the user. The prover will convince the verifier that it knows a valid solution to some instance of a computational problem. Now, the prover will perform a computation and then produce the result of that execution, as well as a proof that that computation was correctly executed. And so both that execution result and that proof will be sent to the verifier, who will check that the proof was indeed executed correctly. The proof to verify that the computation was correctly executed. So looking at that interaction in this diagram here, the verifier will say, I have an entry X, I have a function F, X is an input to F, and the verifier will ask the prover to compute the result Y over here. And the prover will compute both that result Y as well as produce a proof W. And both the result Y and W will be sent back to the verifier for the verifier to check that if the proof is valid. Now, this diagram over here was taken from the Education Hub's course on a high-level Intro to Zk and Snarks. If you want to learn more about verifiable computation, check out that lecture, which I linked right over here, and I'll also put in the description. Now, when we say computational problems, what do we really mean by that? So some examples include the problem of factoring. So finding the prime factorization of a given number, which is a common toy example that's used a lot in zkVMs. Another example is finding the discrete log of a given expression, and that ties a lot into the discrete log problem. And another could be, I know the private key that's corresponding to a public key, and I want to prove that. That ties into the challenge response protocol in public key cryptography. If you want to learn more about challenge response, there's also a separate lecture about that in the course, so be sure to check that out. And this is also how your browser authenticates a site certificate. So data that has been encrypted with a public key can only be decrypted with its corresponding private key, vice versa. That's another example. And a fourth example is the validity of a signature from an ECDSA. That uses keys from elliptic curve cryptography, which also ties into the application of signature verification. So those are just some of the examples of computational problems that we're speaking about. Now, in convincing the verifier that a computation was done correctly, why can't you just, rerun the program and produce a dump of the entire execution of that program, or better yet, just reveal the solution? That's a lot easier than doing all of this work by having the verifier having the prover produce an execution result and a proof, and then sending both of those to the verifier to check. So why can't you just simply do these things instead? Well, there's a couple of reasons why this is not such a great idea. For one, the resulting proof for the entire execution of the program would be way too long. The verifier would have to replicate the entire computation that's done by the prover, and that's pretty counterintuitive because we're essentially doing double work. The verifier also may not have the computational resources to do that to begin with. So for example, in zkMIPS specifically, we'd have to rerun the program to produce that entire sequence of states, and that would be way too large for the smart contract who acts as our verifier to verify. So this is not possible. And the point of having a verifiable computation is for all the difficult, long work to be outsourced to the computationally more powerful prover, while the verifier's work is as simple as possible. So ideally, we want this proof to be short and also easy to verify, or in other words, succinct. And another reason is that the prover may want to just keep the solution a secret. The privacy component over here is known as zero knowledge, or ZK. And for ZK-specific proofs, the proof does not reveal any additional information about that solution. So those are the two main reasons why you can't just simply rerun the program. We need to consider both the ZK aspect and also the succinctness aspect. I'd also like to emphasize that a lot of projects nowadays use ZK to mean privacy when they really mean succinctness. ZKM specifically is focused on the succinctness aspects of the proof, not the privacy. And when we're applying proofs of knowledge to blockchain applications, there's a few properties that we need to consider for the proofs. So one is non-interactiveness between the prover and verifier. This makes it so that the parties involved can be untrusted, and it also allows a larger number of observers to verify the proof, not just one verifier. Also, we have the succinctness property, which we previously saw. That just means that the proof should be short. The ZK property is optional. And the types of computational problems that these proofs of knowledge can apply to are, for example, one with transition functions for L2s. We see this a lot in ZK rollups. Essentially, the L1 acts as the verifier, while the L2 acts as the prover. So the L1, for example, could be Ethereum. It's like a computer in the cloud, so it could be very slow, very expensive at times. Scalability is an issue. And the idea here is to outsource these computations off-chain from an L1 onto an L2, and the L2 would send the resulting new state with an accompanying proof back to the L1. Another example is the execution of smart contracts, which is the main function of Zk EVMs. Those smart contracts are typically written in Solidity, and the EVM verifies the execution of that contract. Now, a third example is the execution of off-chain programs as seen in zkVMs. So in ZKM's case, an off-chain MIPS program is given, and zkMIPS will verify the execution of that program on-chain. Now, the computational problem within ZKM here is to verify the correctness of the execution of a program, and the solution comes in the form of a proof of correctness, and that really comes in the form of an execution trace. The execution trace you can think of as a complete record of the computation that's executed from running the program. So it's commonly represented as a table with columns representing the CPU variables and the rows as the different steps of the computation. The verification process of this execution trace involves checking that each row of that trace matches the respective instruction of that program. So some examples of programs to verify on zkMIPS within the blockchain area For example, if you want to verify the correctness of some blockchain-based transactions or some smart contract function calls, some transactions on rollups, those are just some examples of programs that zkMIPS can verify. Now that we've covered verifiable computation, let's go into the next keyword here, zkVM. But to understand what a zkVM is, we first need to answer what a VM, or virtual machine, is. You can think of a VM as a kind of program that runs other programs. For example, EVM, which is Ethereum virtual machine, it's a type of VM that can run Ethereum smart contracts. So in a VM, we have a program that's compiled down to VM readable code or machine code, as well as an input to the program. So both this input and the program are fed into the VM, and a final state of that program will be outputted as a result. Now for a zkVM, it's basically just the VM with a few extra components. You can think of it as a ZK circuit that runs a VM in order to prove that a program was correctly executed, which is needed in our proofs of knowledge. So in addition to the input and the program that's compiled down to machine code, and just to note, the format of that compiled program is dictated based on the choice of the ISA or the instruction set architecture. So in ZKM's case, that's MIPS. In addition to this input, as well as the program, there's also the witness. The witness is a collection of values that the verifier does not read. So either because the prover wants to keep them private, so they act kind of like secret inputs, or because they're just too long for the proof to be succinct. So the verifier does not read them at all. Now the input, the program, and the witness, all three are fed into the zkVM, where in addition to the output of the program, the final state, there's also a proof for the correct execution of the program that's generated. Now, why would you use a zkVM? Well, the alternative is to write a ZK circuit. A circuit is an encoding of a program into what are called constraints that prove the correct execution of a computation. And in a circuit, there is an input and a program that's written in a specialized language for ZK applications. For example, you may have heard of Circom or Noir or Leo. Those programs need to be written in those specialized languages. So both of these, the program, the input, are fed into the circuit, where, like the zkVM, a final state as well as an accompanying proof are outputted. In this case, even though circuits can be highly optimized and are generally efficient because the circuit is going to be exactly what's required for the program and there's no extra components that you have to deal with, like memory, for example. Even though the circuit has that benefit, it's generally better to make the actual circuit constructed in VM, as we can see with our zkVMs. Because looking at these differences between a circuit and a zkVM, with a zkVM, instead of a circuit being equivalent to a program, we can have a circuit that knows how to execute a program. So while a circuit is specific to each program and a special verifier needs to define each time, a zkVM can be thought of as a generalized universal circuit where you only need to define the verifier one time. And another benefit zkVMs have is the ease of adoption. So any developer can use a zkVM because they can just use their preferred high-level languages like C, Rust, Go, since all those programs written in those languages will be compiled down to machine code, so it doesn't really matter what language you're using. Whereas in circuits, developers need the additional knowledge of, say, writing in specialized ZK languages. But in addition to that, they need to have the knowledge of writing circuits, defining constraints. They need to have some background knowledge as well in cryptography. So there's a pretty steep learning curve involved for the circuit-based approach. In zkVMs, you don't really need anything additional to learn before you can start implementing. So for this reason, a lot of zkVMs emphasize the benefit of using the time to build applications and not circuits. zkVMs additionally also have a generally easy path to recursion. So after taking the first program, you can take the proof that's generated and pass it as an input, run a verification program with that proof, and then get another proof that proves that the first proof was correct. So that recursion aspect is present within zkVMs, but it's a lot more difficult within circuits. And if we compare zkVMs to Zk EVMs, one of the main benefits for zkVMs is that they are built on well-established and also unchanging instruction sets like MIPS, which ZKM uses, whereas EVM frequently undergoes some opcode changes, and that may lead to the ZK circuits changing as well. In terms of stability, Zk EVMs can only support Ethereum Geth, but zkVMs can support programs written in many languages, and for that reason can also have applications in non-blockchain scenarios, which Zk EVMs do not offer. So those are kind of the main value propositions for using zkVMs. Going into the next part, let's look into MIPS and why we're using this specific instruction set architecture. So ZKM uses the MIPS 32 microarchitecture, and all programs, no matter their language, will be compiled to the machine code MIPS programs so that it's understandable to the VM. And looking at the benefits of MIPS over here, it first has a stable design, so there's no need to frequently redesign the ZKP circuits. And unlike EVM bytecode, which we mentioned just a little while ago, which may undergo some frequent opcode changes, RISC-V, or like RISC-V, which has custom instructions, MIPS has a more streamlined set of opcodes compared to the EVM bytecode and also RISC-V. MIPS itself has a very strong industry presence, and it's very well established, has been around for around 4 decades, and overall has a pretty mature ecosystem compared to some of the other ISAs in the market. Now on to our last part. We'll take a deeper look into zkMIPS specifically and how it works. Now this is a broad step-by-step overview on all of the components that are involved within zkMIPS. And this process can be separated into 3 different parts. The first part is the program execution, then there's the proof generation, and then the last part is the proof verification phase. Now, in our first part of program execution, we take a program which is written in a higher level language like Go or Rust. And that program is fed into the MIPS compiler, which compiles a program into a MIPS ELF binary file, and that's basically the executable format for MIPS. So the ELF file will be readable to the VM by converting that source code that's written by the developer into machine code. The ELF loader will then load the MIPS ELF binary file into the MIPS VM. And the MIPS VM will execute the compiled program and generate an execution trace for the prover to use in order to prove the program. Now, in this first step of running the program and collecting the trace, it's important to note that any high-level language can compile down to MIPS, and we'll get a sequence of the MIPS instructions as a result. So how this looks like is that after each instruction is executed, which we can see on the left side table, we'll get a value for each register that's based on the instruction. So for example, in row I, the data operation that we're using is addition. The instruction is basically saying add the value from register 5 to the value in register 6, and then put the result of this addition in register 7. So we can see over here, 13 plus 21 is 34. And after going through all of these instructions, we'll get the trace table, which is shown on the right. Remember that the trace table is a representation of the execution trace. And then the prover will take that generated execution trace and check that the program was executed correctly, and then generate a proof for that correct program execution. There are 4 main proof layers involved in this process: Stark, Logup, which is a form of Stark, Long, and then Grot16. We'll briefly go into the functions of each one. So over here, first, the execution trace, which we will see on the left side, it's split into individual segments, which is shown on the right here. Segments are just small sequential executions from the program. And with these segments, they're then divided into modules. And modules are just smaller executions from those segments. Splitting the program into segments and then into modules really helps with the succinctness aspect and lowering the overall computational expense. So from here, the instructions of each segment are divided into these 4 modular tables: arithmetic, control, logic, memory, depending on its operation. So if the operation is arithmetic, as we can see, these ones involve arithmetic operations, those instructions will go into the arithmetic table. If it's logic-based, go into the logic table, so on. And now we reach this first layer of this proving stack, Stark-based proofs. The modules are really proven independently with a protocol called Fry, using these Stark proofs. So as a result, we'll have arithmetic, memory, logic, and also control proofs that are generated. Now, in this next part, we use a lookup scheme called Logup, which basically shows that a segment is contained in the modular table, and it's used to prove that the program instructions were correctly verified in their specific modules. So all of these module proofs, arithmetic, logic, control, memory, they're combined into one single proof for each segment. And then the next part that involves Long, all of these segment proofs from the previous layer are recursively combined using continuation into a single proof called the continuation proof. And this proof will prove the correctness of the entire program trace. And this last part within this proving stack is optional, but for the proof generation process, to enable for on-chain computation after generating the proof, or while generating the proof, this final continuation proof is turned into an EVM-friendly format using Grot16 that basically allows the final proof to be verified on the L1. And I just gave a very brief overview of the prover, but if you want to learn some more details about the proving stack, be sure to check out the zkMIPS white paper and also our blog article about the architecture from our R&D team. So be sure to check out those 2 resources, which I linked here. Now, this final proof that we generate is called the zkMIPS proof, and that shows the correct execution of the entire program after applying Grot16. So most of these techniques that are applied during this proving process, they're really used to decrease the overall final proof size and also the proving time. So in the final part of the zkMIPS proving process, it's the proof verification aspect. Once the final proof has been generated, the verifier will be able to verify the results of the executed program using the proof. So it can check the proof and accept or reject the result. And in our case, the verifier comes in the form of a smart contract. And just as an overview of this process, It first always starts with an end user's action. So the end user will want to prove the correct execution of some program. So for example, maybe the correctness of some blockchain-based transaction that they're involved with. The program that the end user creates will be run in the zkMIPS execution environment. And that program will compile to MIPS so that it's readable for the VM. And then afterwards, it's the proof generation. So zkMIPS proof for the program's correct execution can be outsourced to the proofing service, which we'll demo. And once the zkMIPS proof is generated, a verifier contract will verify the proof. And in the case of proving the correctness of blockchain-based transactions, once the proof is verified on-chain, the transaction is considered to be settled. Now, looking at how this all works in an example, well, ZKM is, just as a note, is building an entangled rollup network where L2s can be used as interoperability mechanisms to facilitate the cross-chain actions without actually having to implement a bridge. In this case, say that we want to transfer 100 USDT between two different networks. So from Ethereum to Avalanche, for example, using this universal L2 system. First, this 100 USDT will be deposited into the Ethereum L2, and then a proof that the 100 USDT was burned on the L2 will be generated off-chain, and that proof will be verified by a verification contract on that destination chain. So in this case, it would be on Avalanche. And the 100 USDT can then be minted and then withdrawn to the Avalanche L1, where the user will receive that 100 USDT on the Avalanche L1. And this diagram, just a note, was taken from ZKM's settlement network page. So if you want to find some more examples of use cases with entangled rollups, be sure to check out that page. Now, our proving service, onto our next part, allows developers to efficiently generate proofs, and it serves as an alternative to generating proofs locally, especially if you don't have the minimum hardware requirements or want faster proof generation. You can use the proving service in those two cases. Now, zkMIPS currently supports Golang programs with support for Rust coming very soon. We encourage developers to build use cases, any that you could think of. For example, maybe performing some action with each valid proof, like with minting an NFT or ERC20. I'll show you how you can mint an ERC20 with a valid proof in our demo very soon. But if you're interested in governance or identity verification, maybe querying some answers from an ML model that ties into zkML, as a transaction verification, the number of use cases here really are endless. Now, going into the demo, we are going to generate a proof with a toy example using a Go program. And that Go program is called isEven. So as you can see here on the left, it's a simple Go program that determines if an input is even. If it is, we'll have a valid proof. If it isn't, the proof will be invalid. And we'll be using ZKM's proving service to generate that proof. And then we'll deploy the proof on a verifier contract to verify the proof. And if the proof is valid, we'll be able to mint an ERC20 token. So that's the process and the steps that we're going to take in today's demo. Now, if you want to follow along, I linked some of the resources we'll be using. So be sure to clone these repositories. There is also a guide for completing the proof generation and verification. And also be sure to have these requirements for Rust and Golang if you're following along. Now, for this first part of the demo, I have this pre-recording here that I will make in 2x speed just to save some time. Over here. So once you've pulled the latest version of the repositories, go to the ZKM prover repository. And for today, we're going to use the isEven program. So create a new program over here. And this is the same program that we saw in the previous slide. So add that to the ZKM prover repository, and you should change your directory into that. I also recommend establishing the path of Go in your bash file so you don't have to do this command every single time you open a new terminal. But afterwards, in our first statement, right over here, this first statement will compile the Go code to MIPS and produce that ELF binary file that the VM can read. So notice that we have that ELF file right over here. That was just generated. And in the next step, over here, we are requesting the proof generation from the prover service. So we're specifying those parameters like our segment size, and then also we have our public inputs, which we use as 6. If you use an odd number, the proof won't generate. Also specifying our endpoints and then our path to our ELF file. Now, if the proof generation is successful, okay, let me go back over here. If the proof generation is successful, we'll get a download URL as an output. So that's this link over here. And if you open this URL, I will just fast forward a bit. If you open this URL, then you will get the content for the proof with the public inputs, and it's in the form of Plonky2 proof. And then afterwards, to start the on-chain verification process, change your directory to the verifier and enter into it. So over here in this command, we are adding the content from the download URL in our proof to a new JSON file called snark proof with public inputs, and that will be put into the MIPS folder under test data as we specified here. So you're basically just moving the proof that you generated to that folder. And then now, as our next step, from here we can build and compile the benchmark program and convert our Plonky2 proof into a Groth16 proof. So remember that turning our proof into Groth16 proof will enable our proof to be verified on-chain. And that step is required if you want to deploy your proof on a verifier contract. And this step does take some time, so I will fast forward a bit over here. And as you can see, these are the outputs that you will get from running the benchmark program. And again, this does take some time, so when you're doing it on your side, be sure to be a little more patient for this step. But once that step is completed, once you've compiled the benchmark program successfully, all the contents in the snark proof with public inputs file will be updated because we just used Groth16. And now you can build the caller file right here and use this to generate an on-chain verification contract using the hard hat ignition, which we're doing in the second command over here. And if it's successful, it should output success. And in our next step, we are using the verifier contract to verify the proof. So first, we should copy the snark proof with public inputs file to the test file under this hard hat folder. So that's what this command is doing. And then we'll start with running the hard hat node using this command, npx hard hat node. This will basically start a JSON RPC server onto the hard hat network so that you can do a hard hat ignition deployment in the next step. We'll also run a hard hat test, and that will test if the proof submitted to be verified. So if a proof was submitted, then it should pass. If not, that means a proof wasn't successfully submitted. So as you can see here, we have successfully submitted a proof. And now in our next command, we are deploying the verifier contract on a test network. We're using Sepolia for this example. And as a result, you'll be able to see the deployed address, which will be outputted. And from now, you can call the contract using your deployed address that was generated. So that's what we're doing in this command. And then you will get the transaction hash for the verified proof as a result. And you'll be able to view all the transaction details for the hash on Etherscan over here. So just fast forwarding this a little bit, we can see that it was a success, and you can view all the transaction details as you wish over here. Okay, so that is for the first part of successfully generating and verifying a proof. Now let's use the verifier for some on-chain actions. In this part, we're going to use the valid proof that we've generated in the previous part and also verified in the previous part to mint an ERC20. So going into the second part of this demo, first we will change our directory to the use cases repository, specifically into the hard hat folder. So that's what we're doing here. And then now we can redeploy the contracts. That's what this command is doing. I also want to mention before completing this step, under hard hat, that folder, there is another folder called test. Be sure to replace the snark proof there with the valid GLOS16 proof that you previously generated, specifically right after you ran the benchmark program. So be sure to replace it with that proof. And then from here, we can see that the new contract is deploying. So that's going to take a little bit of time. Let's fast forward a bit. Okay, right here, we have our contract that's generated, and be sure to replace the contract address that was generated in the caller.go file under this ERC20 token address. So replace it with the contract that was just generated. And from here, be sure to save that. Now you can go to your wallet and import that token address. That's what we're doing in this step. And as you can see, we do not have any minted tokens yet. It shows up as 0 because we haven't successfully minted anything as of yet. But going back, we can, over here, right over here, exiting out of hard hat, but then building and compiling the caller file. And then also, once that is built, you can mint the ERC20 token and also specify the address that you're using. So the transaction hash will be outputted as a result, and you can just copy that, view all the transaction details in Sepolia. That's what we're doing right here. Fast forwarding a little bit. This does take some time. So just doing some fast forwarding. Okay, right over here, we'll see that it says success in the status. Just to note, if you used an invalid proof, it will say proof is invalid or execution reverted. But in this case, since we used a valid proof that we generated and then verified, it will output as success. So now going back, we can see that we have one ERC20 that's minted on this contract, which is pretty neat. Okay, so that concludes our demo where we were able to generate a proof that a given input is an even number using ZKM's proving service, and then deploy a verifier contract to verify that proof. And then the last step, we were able to use that valid proof to mint an ERC20. Now, if you are interested in generating your own use cases and you want to quickly generate those proofs, maybe you don't have those hardware requirements, be sure to apply for a spot on the whitelist right over here at zkm.io/apply. We do have a limited number of spots available, so make sure to do this as soon as possible. And I also included a QR code here for your convenience. And as always, if you have any questions or if you run into any difficulties, join our Discord, tag me or anyone from the team, and we'll get back to you on your question. Other than that, I hope you guys have a great rest of your day. Good luck with the proof generation verification if you're trying this on your end, and I'll see you next time.